Alright guys, we have another question from the third chapter of the Mechanics of Materials by Johnston, and we have this solid spindle AB that is made of steel, and the allowable shearing stress is 12 ksi for the sleeve for the steel, and we have a sleeve CD around it which is made of brass, so different material, and the allowable shearing stress for that one is 7 ksi. We need to determine the largest torque T that can be applied at A if the allowable shearing stress is not to be exceeded in the sleeve CD. So that's the A part of the question. The B part, we need to find the corresponding required value of the diameter ds of a spindle AB. So if we look at here, we have the ds, which is basically the diameter of the spindle AB, or this part that we don't know, and around that we have the sleeve, which has the diameter of 3 inches and it has a thickness of 1/4 inch. So the thickness for this part is 1/4 inch. So as we talked about in the previous video, we have the elastic torsion formula where the maximum shearing stress is equal to the torque times the radius. We show it with rho over the J, and J would be the polar moment of inertia. So here, because all of our surfaces are circle, we know the moment of inertia for circles 1/2 of pi times the radius. We show it with c to the 4. And in case of hollow cylinders, which is the sleeve that we have in here, we have to subtract the radius. So the informations that we have so far is, if we go with the sleeve, we know that the sleeve CD has the maximum shearing stress. So we have this for sleeve. We can find the moment of inertia. We have the radius, and we should be able to find the torque from this formula. And for finding the moment of inertia in here, so we have 1/2 of pi times the outer diameter, and now we have to figure out the outer and inner diameter. So basically we have a hollow channel like this, where we need to figure out the outer radius, which, since we know the diameter from here to here is 3 inches, so this is going to be 1.5. That's going to give us the radius, and the inner diameter is going to be, again, from the center to this distance, which basically is 1.5 minus this thickness, which is 0.25 or 1/4 inch. So that's all we need for finding the moment of inertia, or J. So 1.5 to the power of 4 minus 1.5 minus 25 is 1.25 to the power of 4, and this is going to be in inches squared, inch to the power of 4. So that's our J. Our rho is basically the R, or the outer diameter that we talked about. So 1.5 is our rho inches. And yeah, that's pretty much it. So we can find our T, basically shearing stress times J over rho. So shearing stress from the question, as we talked about, is 7 ksi. So we can multiply this by 1000. We know 1 ksi is equal to 1000 pounds over inches squared. So we can multiply that by 1000 to get it in pounds per inches squared, and we have our J, which is what we found in here. So 1/2 of pi 1.5 to the 4 minus 1.25 to the 4 over our rho, which is 1.5. So let's just see what we get, and what we're going to get from here, pound per inch. So we have 3 inches in the denominator and we have 4 inches squared in the numerator. So we're going to end up with the torque unit, or pound inch. So let's just calculate this. Times pi times 1.5 to the 4 negative 1.25 to the 4. In the denominator we have 1.5. So that's going to be 19.21 times 10 to the 3. Or we can keep this 1000 pound as kip, so 9.21 kip inch. So that's going to be the T that we're looking for, and we know 1 kip is equal to 1000 pounds. So kip is the unit of the force, and KSI is the unit of the stress, or the force over area So that was the A part of the question, and in the B part, we are missing the D here, and we can find the ds based on the same formula. So we have our elastic torsion formula again. It's equal to T rho over J. And now that we have a solid shaft in here, so we can put this one half of rho to the 4 because that's the same diameter. It's not a hollow shaft, so we can cancel one of these, and our formula will turn into, we can bring that up, pi times rho to the power of 3. So since we are interested in our rho, so rho in here is the radius, but if I look at it, the question is asking for the diameter. So that's one difference in here. What we can do here, we can just put ds divided by 2 in here, but let's just find the radius for now. So our rho would be, or rho 3 would be 2t over pi times the maximum shearing stress. So 2 times, we're gonna have the same torsion. We can either go with this unit, but keep in mind if we are going with the pound, we have to be consistent for this one too. So let's just go with the pound. So 2 times 19.21, 10 to the 3 pound inch in here. And in the denominator, we have pi, and we have to find the maximum allowable stress for spindle, which is 12 ksi, so 12 times. So basically our rho would be this value to the power of. So let's just see what we get. 2 times 19.21 times 1 times 1000 over pi times 12 times, again, 1000 here. And we have the whole thing all to the 1 divided by 3. So this is gonna give us the rho, or the radius, 1.006 inch. And again, what we are interested is the ds, which is the diameter. So it's gonna be 2 times rho. So that's gonna be 2.012. Or we can just keep the 3 significant digits that we usually do for these questions. And yeah, that's going to be the answer for the B part of this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.